Hello, welcome to Mine's a Pint Einstein. My name is Marcus Chown and I'm a science writer. I write books on quantum theory and Big Bang. And the Big Bang is the subject of today's programme. Now, perhaps the greatest discovery in the history of science is that there was a day without a yesterday. The universe has not existed forever, but was born 13.82 billion years ago. All matter, energy, space, and even time erupted into being in a titanic fireball we called the Big Bang. That fireball expanded and cooled, and out of the cooling debris, there congealed the galaxies, 2 trillion of them, of which one of them is the Milky Way, where we are. Now, my guest today is Paul Halpern, who is a professor of physics at the University of the Sciences in Philadelphia, and he's written a book now called Flashes of Creation, George Gamov, Fred Hoyle, and the Great Big Bang Debate. And the greatest compliment that I can give Paul is that I wish I'd written his book. I've written about Gamov and Einstein, and it's such a fantastic idea to write about this subject through their eyes from their point of view. So, welcome to the show, Paul.
Thank you, Marcus. And I have to say, I'm a great admirer of your work, and you've written so splendidly about the Big Bang and steady state and nucleogenesis in the past. So I'm really complimented that you like my book.
Oh, well, thanks very much, Paul. Now, what inspired you to write this book?
Well, I've always been a fan of both George Gamov and Fred Hoyle, and growing up, I read Gamov's book 1, 2, 3 Infinity, and that was really inspiring as a youth when I was a teenager, with all its wondrous accounts of science, with splendid illustrations, very imaginative, looking at the fourth dimension, looking at what happens if you take things and transform them in the mirror. And Gamov was just an amazing science writer. And then later I found out that he was behind the idea of Big Bang nucleogenesis. And I also knew about Fred Hoyle from the competing theory, steady state theory, and I had the privilege of seeing him lecture in Philadelphia. And he really gave an excellent lecture. I heard about his books. I read some of them, Black Cloud, some of his science fiction, and also I was similarly impressed. And then at one point, I was putting down a to-do list in terms of writing projects, and I thought, well, Hoyle wrote an autobiography. Wouldn't it be fun to write a biography of Hoyle or kind of capture his life? Of course, Simon Mitten did that rather recently. But I also was thinking it would be fun to write a biography of Gamov. Gamov has an autobiographical account, but strangely enough, it stops in the 1930s before he did anything with the Big Bang. So I asked Gamov's son why, and George Gamov said, well, he didn't think that he did anything much after he moved to the United States, which really wasn't true. But I had ideas to do biographies of either of them. And then at one point, I was looking for ideas to write a book, and I thought, well, maybe I can combine the two and write about both Gamov and Hoyle.
Well, let's set the scene before we talk about Gamov and Hoyle specifically. Let's set the scene. So, really, in 1915, Albert Einstein comes up with his theory of gravity, which shows really that mass or energy warps or curves space, and that is gravity. Curved space is gravity. And in 1916, he applies this theory to the biggest gravitating mass he can think of, which is the universe, and he makes a mistake. Is that true?
Yeah, so it's Einstein wanted to apply his theory to gravity to the universe as a whole, and he had this preconception. It's funny because he overthrew a lot of Newtonian ideas, such as Newtonian space and Newtonian time, but he had this preconception that the universe must be static, that it must be stable, that only the stars move in the universe, but space itself, of course, must be stable as a whole. So when he came up with his solution to his own equations, he found that the solution was unstable, that if you change the matter distribution slightly, it would collapse or expand. So then he thought, well, I made a big blunder. I made a big mistake. and added an ad hoc term called the cosmological constant. And that term was a bit like scaffolding to support a building that's falling over. It was inelegant. It was not very beautiful, but at the same time, it gave him what he wanted. He wanted a stable universe. Later, he realized that that was a mistake. He could have predicted the Big Bang, but instead he predicted a stable universe, which is not the case. Indeed, the universe is expanding.
So it was left to others in the 1920s to actually see the message in Einstein's equations that he'd missed. It was a couple of physicists, wasn't it, who realised that the universe was restless. It couldn't be static. It had to be in motion.
Yeah. So mounting evidence showed that the universe must be in motion, and that's where, for example, the solutions of Alexander Friedman and Lemaitre showed a universe that's dynamic. And if you eschew the cosmological constant, if you don't consider that, then you get dynamic solutions to the universe, which turned out to be correct.
Right, and then that was, I think, Alexander Friedman and Georges Lemaitre, who was, I believe, a Belgian Catholic priest. So he must have quite liked the idea of a Big Bang because it was very similar to the "Let there be light" of Genesis.
Well, Lemaitre, yes, he was a priest, although to his credit, he believed that science and religion should be kept separate. So he advised the Pope at the time, Pope Pius. He said, do not emphasize so much the religious aspects of the Big Bang. This is science. But the Pope didn't heed his message and gave fully two addresses saying that the Big Bang theory was proof of God's creation and of Genesis. And that stimulated Gamov. Gamov sent the Pope a copy of his book, The Creation of the Universe. Even though Gamov was not a religious person, he was very impressed that the Pope was taking his side.
So that was all theory, but by the late 1920s, by 1929, we actually discovered that the universe really was expanding. Who was that? Who was responsible for that?
So we give credit to Edwin Hubble for his discovery in 1929 that the galaxies in the universe, all of them except the nearby galaxies, are receding from our galaxy. So Hubble came up with that idea by combining two bits of data. One piece of data had to do with distances, and he used what are called Cepheid variable stars as standard candles. A standard candle means something that has a known amount of energy. So it's kind of like if you're walking down a dark hallway and you saw a torch ahead of you, and you saw how bright the torch was. If it was extremely bright, you might think, oh, well, it's right in front of me. And if it was very dim and you knew that the torch had all torches had pretty much the same power, you would think, oh, it's very far away from me. Similarly, if you see a Cepheid variable star and it's putting out a lot of power, it seems to be putting out a lot of power, then you say, well, it's closer. If it seems to be dimmer, then you say it's farther away. So that's one bit of information. And that was Henrietta Leavitt's discovery. She was somebody who worked at Harvard as a calculator, calculating data, and she came up with this famous law that you could determine the power of a Cepheid variable star from its periodicity, from how often it flashes, which was amazing. And the other bit of information actually came from some of the data of somebody named Vesto Slipher, who determined that you can use redshifts, which are a way of determining speed. It's a little bit like the idea that when a fire engine is moving toward you, it sounds higher and higher pitch, and when it's moving away from you, it sounds lower pitch. Similarly, light does the same thing, and light, if something's moving away from us, it shifts towards the red end of the spectrum, and if it's moving toward us, the source is moving toward us, it shifts toward the blue end of the spectrum. And what Slipher found in the early 1920s and Hubble used in 1929 is that all of the galaxies, except for Andromeda and a few nearby galaxies, were redshifted, meaning they're moving away from our galaxy. So unless our galaxy did something really horrible to offend all the other galaxies and to make them flee from us in terror, it must be, scientists concluded, evidence that everything is moving away from everything else, which means that the universe is expanding.
So kind of all the galaxies are flying apart like bits of cosmic shrapnel in the aftermath of this big explosion in the past. And I should say, Ernesto Sniper was a mule driver, wasn't he, on Mount Wilson? And I just to add my sort of sixpence worth, from my kitchen when I lived in Pasadena when I was at Caltech, I could see Mount Wilson where Hubble actually discovered that the universe was expanding. So that was a real thrill. Now, if we get to Gamov, Gamov was we ought to mention, Gamov was a Ukrainian. He was born in Odessa. So, and he escaped from Stalin, I think in the early 1930s. He went to America, and he was interested, wasn't he, in trying to find a furnace that had forged all the elements. So the idea, I think, was that, the universe had started off with the simplest element, maybe a hydrogen, imagine it as a single Lego brick, and all the other heavier elements, carbon and oxygen and whatever, had been assembled from this original Lego brick in a hot furnace. And is it true he was the first person to take the expansion of the universe seriously and realize that if the universe was expanding, it must have been smaller in the past. And when you squeeze things into a small volume, like you squeeze air in a bicycle pump, it gets hot. And so he thought that it was the furnace of the Big Bang that forged the elements in our bodies. That's the case, isn't it?
Yeah. So Gamov, as you mentioned, he was born in Ukraine, in Odessa, and he went to university in St. Petersburg, which became Leningrad and is now back to St. Petersburg. And his one of his great teachers was Alexander Friedman, and much to his dismay,
Friedman, who was one of the people who came up with the Big Bang idea.
That's right. So Gamov learned about the Big Bang from Friedman himself. Friedman taught a course in general relativity, and Gamov wanted to work with Friedman, but then Friedman died of typhoid at a young age. So Gamov was really distraught. So he ended up working in quantum physics, which wasn't such a bad thing because that enabled him to make his big breakthrough with quantum tunneling, which gave him his fame to show that nuclear fusion can take place through a tunneling process. And that led him to discover how hydrogen can fuse together through a number of steps into helium. And Hans Bethe took up that process and then made some discoveries in that area. But people by the late 1930s and early 1940s understood how the sun could produce helium, but how the higher elements are produced was a big mystery.
So can I bring in Hoyle? Sorry, can I bring in Hoyle at this time? Because whereas Gamov was thinking that it was a hot Big Bang, he was the first person to realize that the Big Bang was hot, had 40 elements. Hoyle was thinking it was stars, wasn't he? And the reason that Gamov, I believe, thought of the universe was because Eddington earlier on had thought that stars were too cool to forge the elements. As you say, Gamov then realizes that quantum tunneling changes everything. So Gamov was looking for a furnace to build all the elements in our bodies in the Big Bang, and Hoyle was looking for a furnace inside stars. And isn't it true that in fact the answer is they were both right?
Yeah, that's amazing. Yeah, it is amazing that Gamov wrote the beginning of the story, as I say, and Hoyle wrote the end of the story. And both of them were right in some aspects. Gamov thought that he could explain all the elements, as he wrote in a letter, from alpha to omega. And he was interested in the Greek letters, which I'll mention.
Yeah.
The paper was the alpha, beta, gamma paper, or alpha named after Ralph Alpher, Hans Bethe in absentia, and George Gamov. So he was kind of making a play on the Greek letters. But in that paper, he tried to say, he and Ralph Alpher, who was a student, tried to say that the Big Bang was hot enough to produce all of the chemical elements up to uranium. And unfortunately for their theory, there was kind of a stumbling block in this ladder of building the elements, that it was impossible to build carbon that way. So carbon, which is essential, of course, for life, cannot be built up in the Big Bang. The Big Bang cools down too quickly. And it was Hoyle who came up with the answer that carbon is produced in the dying cores of massive stars. And then from that point on, as the stars contract, higher elements are formed.
So actually, sorry to interrupt you there. So in fact, most of the elements most of the elements were actually made inside stars, which was so Hoyle was correct, but they only account for 2% of the ordinary mass, and about 98% of the light elements were made in the Big Bang. Can we just get on to the Hoyle's theory now? The universe is expanding, so it looks as if it was smaller in the past and there was this Big Bang. However, Hoyle was very wedded to the idea of the universe existing forever, and he came up with this steady state theory. And didn't he get the idea from a movie? Wasn't it a movie he saw in Cambridge in 1948?
Yeah, so Hoyle and his two friends and colleagues, Herman Bondi and Tommy Gold, were in Cambridge right after the war. They had worked in the war effort and then became interested in astrophysics. And one day they were trying to take a break from their science, and they went to a cinema in Cambridge. And at that cinema, they watched a film called The Dead of Night, which was a horror film. And the strange thing about the horror film is it is about somebody who goes to a country house and has this strange feeling that he had been there before. He felt like he had dreamt about the house, and he felt like something horrible would happen in the house. And everybody else in the house says, no, 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 you're worrying too much. But then they go on and tell these ghost stories, these horrendous stories, which culminate in this gruesome dummy, a ventriloquist dummy, who's this evil dummy. So, and I'm not going to give away the whole plot, but something horrendous happens at the end. You have to watch the movie to find out. And then at the end of the film, the main character wakes up. He realizes that it had all been a nightmare. And then somehow he sort of blanks out about the nightmare and gets a phone call from the person who has the house in the country house and invites him to a gathering. And he goes there. And it turns out that the film is cyclical, that the film has a plot which keeps happening again and again. He has to experience this nightmare again and again. And after seeing the film, they went back to Bondi's flat in Cambridge. And while drinking some brandies and relaxing, Gold said, hey, what if the universe is like that? What if it just keeps repeating itself? Well,
they admitted that the universe was expanding, but they thought that maybe as the galaxies got further and further apart, new material fountained into existence in the gaps, which congealed into new galaxies. So rather than having matter all created in one moment in the Big Bang, they had it continuously created. So their prediction, I suppose, was that the universe, the steady state theory, the universe would always look the same at all times. It wasn't evolving at all. But then I suppose the important thing is it was falsifiable, wasn't it? They come up with this alternative to the Big Bang was falsifiable, and it was falsified, wasn't it?
Well, yes, it's falsifiable, but that's the brilliance of the idea. Hoyle always felt that the Big Bang theory was a bit of a cop-out, that you're saying put all the problems in the past, that you want to explain everything by something that happened 13.8 billion years ago, or at that time it was thought to be only a couple of billion years ago, wrongly. So Hoyle thought, well, why come up with a theory that's not falsifiable when you can come up with something which is immediate, that you can test immediately? Of course, Hoyle did not realize that there are ways of testing the Big Bang theory. He thought, well, you can look at the current state of the stars, but he didn't realize that there was relic radiation left over from the Big Bang that would prove to be the smoking gun as proof. So,
And that's the killer, isn't it? That's the afterglow. So the fireball of the Big Bang was contained in the universe, and the universe by definition is all there is. So the fireball is still around us today, greatly cooled by the expansion of the universe in the last 13.82 billion years. And it was discovered by accident, wasn't it?
yes, that's right. So in 1964, there were two scientists at Bell Lab, radio scientists, who were working in Homedale, New Jersey, and they were working using a horn antenna, which was given to them by as a leftover communications satellite detector at their company Bell Labs, and they repurposed it to look for radiation in the halo of the Milky Way, and they were trying to find some signals from the Milky Way. They were not using it to explore the universe, but then at one point they started noticing a hiss in their detector, and that hiss would not go away. And no matter what they did to try to subtract the hiss or to try to reorient the antenna, the hiss was still there. And at one point, they thought it might be the droppings of pigeons, which they called white dielectric material. And they carefully cleaned up the antenna and trapped all the pigeons. And the pigeon traps are now in the Smithsonian Institution in the United States, by the way.
And I think they sent the pigeons in the company mail to another AT&T site. They were
very
Homedale.
humane.
Yeah. But unfortunately, they came back because they were homing pigeons, and in the end, they had them shot, which is terrible, really. They were shot for science. But then again, in the end, here we have two pigeons on the screen, not the pigeons, of course, but two pigeons. But in the end, in 1978, Penzias and Wilson, who discovered this, and at one point thought it was the afterglow of, the microwave glow of pigeon droppings, did win the Nobel Prize, didn't they, for it? So that was probably the death knell of the steady state theory, really, wasn't it?
Yeah. So once they came up with the idea, once they heard the hiss, they didn't know what it was, but they had a friend named Bernie Burke, who was another radio astronomer, and Bernie Burke happened to know somebody who went to a lecture by Jim Peebles at Princeton, and the lecture was about trying to detect leftover radiation from the hot early universe. And so Penzias found out that Bob Dickey's group in Princeton was working on building a radiometer to try to detect radiation in the early universe. So Penzias called Dickey. Peebles and two other associates, Roll and Wilkinson, were in the room having a brown bag lunch. And all of a sudden they heard Dickey saying, talking about a radio telescope and picking up a hiss. And they sort of got an inkling as to what it was. And then finally, Dickey hung up the phone and said, "Boys, we've been scooped. Somebody's found what we were looking for."
So the evidence of the Big Bang is all around us, really. I mean, not only is the universe expanding in the aftermath of some big explosion in the past, but there is this afterglow of the Big Bang. I mean, if we had microwave eyes, because they picked up microwaves, and we were to look out at the universe, we would see the entire universe glowing like the inside of a light bulb. I think isn't it something like 99.9% of the photons, so these are the particles of light in the universe, 99.9% are tied up in this afterglow of the Big Bang, and only 0.1% in the light of stars and galaxies. It's the most striking feature of our universe. So that in a way kind of killed off the Big Bang, the steady state, you would think. Ironically, wasn't it Hoyle, who never believed in the Big Bang, who actually coined the term Big Bang?
Yeah, that's right. So in a 1949 BBC radio broadcast where Hoyle was comparing theories, and this is before Hoyle really knew about Gamov. He knew about the Lemaitre idea of the universe starting very small, and Hoyle used the term Big Bang, which I find somewhat disparaging. And although I noticed, Marcus, you talking to Hoyle, and he insisted that it was not a very disparaging term.
That's right. I mean, Hoyle, I did know Fred Hoyle, and he always said that he coined it not as a term of, he wasn't ridiculing the Big Bang. He was grasping around for some phrase that he could use to describe this competitor to his steady state. So, but it's a bit ironic that he names the theory that he never actually
But I think,
wanted.
just that said, I think Hoyle's personality was such that he liked to always present a battle between ideas, and he liked to present himself as the objective person. So I think it was in his interest to say he was not putting down the Big Bang, because he was trying to suggest that there should be an equal battle between the two theories, and that the Big Bang people were the ones who were rather mean for dismissing the alternative. And he wanted to show that he was not dismissing the alternative, but that more people should take his ideas seriously. And he said that until the end of his life. In fact, he in his final book, published shortly before his death, he showed a picture of sheep following each other in a herd, and he said these are certain Big Bang theorists. I'm not going to name any names, but they all follow the herd.
Right. Let's just talk a bit about Gamov and Hoyle and their personalities, and then get back on to where we are with the Big Bang Theory today. But both Gamov and Hoyle were larger than life characters, weren't they? I mean, can you tell me about that and what they had in common?
Well, they were both Renaissance individuals. It's pretty remarkable that they were both famous, so famous as scientists and so accomplished as scientists that arguably either of them could have won the Nobel Prize. And Gamov died fairly young, so perhaps if he had lived longer, he would have won a Nobel Prize. And Hoyle, there are various reasons why he didn't get the Nobel Prize. In his later years, he was working on certain fringe ideas, so people might have been a little bit careful not to award him the Nobel Prize because of these fringe ideas. But both of them were potentially Nobel Prize winning scientists, yet at the same time, they were both award-winning science writers. They both won the Kalinga Prize, given out by UNESCO for science writing. And that is absolutely remarkable, because today, I would say they're excellent science writers, such as you, Marcus, and they're people who are who would qualify for the Nobel Prize. But it is very, very rare, perhaps almost impossible these days, to find somebody who you could equally say would qualify for a Nobel Prize and qualify for a top science writing award.
And Hoyle wrote science fiction as well. He wrote science fiction novels which were highly successful.
That's right. So Hoyle could have made a career as a science fiction writer. You know, just on that, he was competing with people like Ray Bradbury, and he met Bradbury. He met Arthur C. Clarke, and he was in that league. He wrote screenplays, A for Andromeda.
Well, didn't he actually discover the actress Julie Christie, because she appeared in the drama A for Andromeda based on one of his books, and I think he always said that he started off her career.
Yes, he was a talent scout, and so both of them are in some ways cinematic figures. They both love the cinema. Hoyle grew up in the cinema because his mother was a piano player for silent films, and he would sit in the cinema and listen to his mother play while watching the films, and that's how he learned how to write from the cue cards or the credit cards for the silent films. And Gamov always loved westerns, and in fact, everybody called him Joe, spelled Geo, but pronounced Joe, and he used to say that was named after a cowboy, the good guy in the movies. So one way that they projected their ideas very well is they are both extremely dramatic, very cinematic. Gamov loved puns and pranks. Hoyle wrote operas, so he wrote the libretti for 2 operas. So they were remarkably diverse figures. They had so many different interests, not just science.
I'll just pick you up on that thing about the Nobel Prize, because I think Hoyle was over. I mean, I think Jacob Bronowski said a genius is someone with two good ideas, and Hoyle certainly had. I mean, Gamov certainly had two good ideas, and so did Hoyle. One was he figured out how all the elements in our bodies were forged inside stars, and the second thing was the steady state theory, because it was falsifiable. It was science.
Hmm.
But Hoyle always thought that he didn't get the Nobel Prize for nuclear synthesis, which is the buildup of elements inside stars, because he criticized the Nobel Committee. And that was because he was at Cambridge when Jocelyn Bell, a student, a PhD student, discovered pulsars. These were pulsating neutron stars. And it was about a week afterwards that he discovered that her name had never been mentioned by the radio astronomy group. And he realized that it had been a student. And then when later years, her supervisor got the Nobel Prize, Tony Hewish, for pulsars. He wrote a letter to the Times in London saying this was, disgraceful. Incredibly, there have now been 3 Nobel Prizes for pulsars, and not one of them has gone to Jocelyn Bell, or Jocelyn Burnell, as she's now known. And so he always thought, Hoyle, that it had been his criticism of the Nobel Committee, this is what he was told, over Jocelyn Bell, that was the reason he didn't get the prize. And of course, I happened to be at Caltech when Willie Fowler, who worked with Hoyle, got the prize. And of course, that created they were friends, they've been great friends, but I don't think they communicated much afterwards. It created a real wedge between them, because Fowler knew that if it hadn't been for a visit of Hoyle to Caltech in 1953, he would have been a run-of-the-mill nuclear physicist. So yeah, that's a real shame, isn't it? And Gamov, do you think Gamov should have won the Nobel Prize for what particular piece of work?
Well, certainly for the idea of using quantum tunneling to explain fusion,
Yeah,
and also for Big Bang nucleosynthesis. So it's two, as you said, it's two great ideas. He
two
certainly.
great. Yeah, he
But,
certainly had them, and there was this similarity that they kind of, they never got blinkered to a certain field. Now we've got, for instance, we discovered the Higgs particle at CERN in Geneva in 2012, and we've got maybe 10,000 particle physicists in the world stuck because nothing unexpected was found. But Hoyle and Gamov appeared. It seemed that they were able to rise above the scientific fray, look down on a scientific landscape like kind of seagulls, and see where there was an area where progress could be made. So they were constantly dipping in and dipping out. And that's such an unusual skill that they both had, because didn't even Gamov contribute to genetics?
so yeah, so they were both in some ways a bit impulsive, and Gamov's impulsivity came about. He would come up with an idea and come up with a simple solution to it. So with the quantum tunneling, he came up with it in one day and told the idea to Eugene Wigner the next day. He took the Schrodinger equation and atomic physics and applied it to nuclear physics, did a quick calculation, and came up with the idea of how protons neutrons can tunnel to overcome the barrier between them, because two protons, of course, have positive charge and they have an electric repulsion. So you have to get them through that barrier in order for them to be close enough to feel the nuclear force, the strong nuclear force. So that Gamov came up with that in a flash. And Hoyle's ideas also came to him in a flash, which is one of the reasons I call my book Flashes of Creation, is not just the early universe, but also that these guys came up with ideas, really quickly. Now, it's much harder to do that these days. If you wanted to unite gravitation with the other three forces, that's something that people have been working on for decades. It's doubtful that somebody's going to take out a piece of paper, a pen and a piece of paper, and do a quick calculation and say, hey, this is the way to unite the four forces of nature. So things are done in much bigger teams these days and take a lot longer, unfortunately. Back then, 1920s, 1930s, 1940s, it was a lot easier to do what are called seat of your pants calculations, do quick calculations and and come up with revolutionary ideas.
And one of Hoyle's techniques, I think, was to fire lots of shots on the understanding that a few would be on target. And this made him a bit of a controversial figure. But of course, Einstein himself was wrong on many things. In fact, he's probably the prominent physicist who was the most wrong. So, that is a kind of a way of being a productive physicist. If you don't fear being wrong, and Hoyle and Gamov didn't fear being wrong, did they?
Yeah. So Hoyle once said that he'd rather be interesting and wrong than boring and correct. So he told that there was a television show in which he and Richard Feynman, were filmed in Yorkshire, walking around a village and then going into a pub. And it's very interesting, their dialogue, because Feynman said you really want to get at the heart of nature. And if nature says something, experiment says something, you need to listen to it and change your theory. And Hoyle disagreed and said, well, sometimes it's better to have a theory that's interesting and an alternative. So Hoyle felt that as long as there could possibly be a shred of evidence for the steady state theory, even if it's only meager evidence, it's better to advocate for the alternative than to go with the mainstream.
Yeah, so they were both like that, but they ended up really both had relatively sad endings, didn't they? Gamov was an alcoholic, and he had liver disease, and he died relatively young. And Hoyle, that didn't happen to him. He lived well into his 80s, but he was quite isolated because he's pointing out, for instance, that Jocelyn Bell had not won a Nobel Prize was one of the reasons why he was estranged from Cambridge. And he lived in the Lake District, didn't he, in an isolated place. So, and without being able to interact with scientists on a daily basis. And so they both really kind of petered out, didn't they?
Yeah. So at one point, Gamov moved from his home institution, which was George Washington University, and moved to Colorado. And that was fine. I mean, it was beautiful out there, but he had less access to the people in Washington, D.C. who were doing things close to his area, such as the Carnegie Institution, which is where Vera Rubin was, and people were doing work in astrophysics. And there's Johns Hopkins. They were doing a lot of work in astrophysics. That's where Alpha and Herman were. So Gamov somewhat isolated himself by going to Colorado, even though University of Colorado is a fine institution. But at that time, there wasn't the internet. So you needed to rely on libraries and on waiting for journal subscriptions to arrive. And unless you were in the heart of things, you were somewhat isolated. Hoyle was even more isolated because he left Cambridge well before his retirement age. And there was a dispute over the institute he founded. And he submitted his resignation, which was really rather shocking because he could have stayed a few more years and retired honorably, but he left before his retirement age, and then went to the Lake District. And he had some associations with other universities, such as a university in Wales, I think Cardiff, and he had an association there. But he pretty much worked on his own, and he pretty much worked with just one or two people, and just came up with his own ideas about how life was created in other parts of the universe, very, very far from his field of research.
So he thought life came to Earth on a comet or whatever, didn't he? That life on Earth was seeded from space in order to explain how life maybe had got started so quickly on the Earth. It got started about 4 billion years ago when the Earth was just cool enough for life. So it obviously was a simple process or an easy process, and yet we've been unable to do that in a laboratory. So he squared that circle, didn't he, by saying that life came from space. Just I think we'll move on and talk about the Big Bang now and where we are. But I can see we've had a number of questions from viewers. One of them is the question, what is the universe expanding into? And I might just say that the Einstein's theory basically describes every point in space moving away from every other point. It doesn't say anything more than that. And the universe could definitely be infinite in extent. It could be infinite in extent, with every point moving away from every point, or it could curve back on itself like like the two-dimensional surface of a ball does. So it's not really expanding into anything. And would you add anything to that, Paul?
Yeah. So the universe doesn't have a center. So the observable universe has a center. And when I give talks, I like to tell people wherever I am at. So if I'm giving a talk in Princeton, I'll say the observable universe, the center of it is at Princeton. And that's because the center of the observable universe is wherever you're located by definition. But the actual universe, if it is infinite, has no center. Even if it's finite, we don't believe that our galaxy has any special place in the universe. It's just an average galaxy in the universe. So any part of the universe is equally the center, which means there's no real center of the universe. So there's no place the Big Bang actually happened.
So basically, when we talk about the observable universe, it's because the universe was born. So the universe was born 13.82 billion years ago, and that means we can only see the galaxies whose light has taken less than 13.82 billion years to get to us. Galaxies whose light would take 14.82 billion years to get to us, another billion years, well, their light is still on its way. We haven't seen them yet. So this creates a horizon around the universe, and it's kind of like the horizon at sea, isn't it? That we know there's more ships over the horizon, and we know that there is more of the universe over the universe's horizon. And within that bubble, bounded by this light horizon, there are 2 trillion galaxies, and that's what, Paul, we call the observable universe, don't we? So
that's right. Yes, it's the part of the universe that our telescopes can potentially see.
And one of the incredible things is that we can actually see to that edge. I mean, here we are, a jumped up ape. We arose on an African plain 3 million years ago or whatever, and we can actually see to the edge, or we can see basically the afterglow of the Big Bang, which is at the edge.
I would say close to the edge, because
close to the edge.
Yeah, right when the photons were emitted. I'm hoping that eventually gravitational wave detection can see even further back.
Yeah, and of course, on something slightly connected but not that connected, the James Webb Space Telescope was launched on Christmas Day, and that has the potential to see an awful lot further back in time than we've seen before. So at the fireball of the Big Bang faded, didn't it? It faded. If there's no one around to see it, but it faded into invisibility, and the universe was dark for a long time, and the universe doubled in size, and it doubled again, and it kept doubling in complete darkness. But in all that darkness, matter was swirling around and congealing because of gravity, and then suddenly, all over the universe, stars switched on. Like lights on a Christmas tree. And those first stars we haven't actually seen yet, but I think the James Webb Telescope has a good chance of spotting them.
That's very exciting to see the first stars, because it's still a mystery how the supermassive black holes in galaxies were formed. And there's some idea that the first stars were enormous and all made of hydrogen gas, and lived out their lives incredibly quickly, and then produced in their collapse massive black holes. And perhaps those black holes fused together and formed the supermassive black holes that form the cores of galaxies today.
I think, yeah, that's one of the great mysteries, really, isn't it? I mean, it was basically the Hubble Space Telescope, which was the predecessor of the James Webb. James Webb hasn't really opened its eyes yet on the universe. It's out beyond the moon. It's a long process to make sure it works before it starts operating. But it was the Hubble Space Telescope that found that pretty much, well, essentially every single galaxy has a supermassive black hole in its heart, including our own Milky Way. We've got a little tiddler in our in our galaxy, and we've got pretty much no idea whether they range in mass from, well, they range up to 30 billion, 40, 50 billion times the mass of the sun, and we've got no idea what they're doing there. Whether they were the seeds around which galaxies formed, or whether galaxies formed and then the massive black holes formed in the center. But as you say, Paul, we look back further and further in time with telescopes like the James Webb, we actually see these supermassive black holes are already very large. So it's becoming a severe problem for cosmology and astrophysics to try and explain how they could have got so big so quickly after the Big Bang. That is a complete mystery, isn't it? Now, I mean, people are going to ask about that. I mean, I saw on Twitter today, someone said, will people believe the Big Bang in 100 years' time? And my answer to that is probably yes. And the reason is that what we mean by the Big Bang keeps changing. So initially, the Big Bang that you were describing in your book, that Hoyle and Gamov were talking about, was really that the universe began in a very hot, dense phase, expanded and cooled, and that's really the Big Bang theory. But because that has actually contradicted, that the predictions of that have contradicted what we've seen when we look out with our telescope, we've had to add all these new bits, haven't we? We've had to add dark matter, dark energy, and inflation. So when we talk about the Big Bang now, we mean the Big Bang plus these three bolt-ons. So where are we with the Big Bang theory at the moment?
So as you said, the Big Bang theory has really transformed in its meaning, and it was found in the 1970s that there were certain predictions of the original Big Bang theory that were off. For example, the original Big Bang theory said that if you had any kind of irregularities in the universe, kind of like if you had a blanket that's wrinkled, the universe could have bumps in it. It could have wrinkles, and the original Big Bang theory says that these would just blow up and become bigger and bigger over time, and that the universe should be this kind of a mess in terms of its shape. Well, rather, we see that the universe is almost completely flat. So we needed something in the beginning of the universe, to flatten it out. And for various other reasons, scientists came up with the idea of an inflationary era in the early universe, an era of ultra rapid expansion in the early universe. And that's part of the Big Bang now. And as you mentioned, we realized that we have a need for something called dark energy, because in 1998, two teams of researchers discovered that the universe is accelerating in its expansion. So there must be some extra force out there that almost acts like an anti-gravity force to push the galaxies further and further apart, faster and faster. So that's a mystery. Dark matter, which is the glue that holds galaxies together and holds galaxies into clusters, is a mystery. So there's a lot out there that's mysterious, but those ideas are still considered part of the Big Bang.
Just put up a picture here, and it shows you how the matter in the universe, and really only about less than 5% turns out to be made of the atoms that you and me, Paul, and the galaxies and the stars are made of. What an astonishing time in the history of science to realize after 300 years, since Newton, that in fact we've been studying a tiny minor contaminant of the universe. I know of that 5%, only about half, 2.5%, if we actually seen with our telescopes. We infer the rest of the other stuff is maybe hot or cold gas between galaxies that doesn't give out light. So it looks like we've got to the stage where we've realized that all the science has been studying is 2.5% of the universe. And I wonder, had Darwin only known about worms and, I don't know, elephants or whatever, but hadn't known about plants and hadn't known about fish, would he have come up with his theory of evolution? And we've come up with this cosmological theory, and initially based on only 5% of the universe. So
that's right.
It's pretty incredible. I suppose one of the things that I think about, and I'm sure you do as well, Paul, is that the Greeks, when they thought that the planets moved around the sun in circles, not around the sun, they moved around the Earth in circles, and because they clearly didn't, they had to keep adding more and more circles, what are called epicycles. So as the planet moved in a circle, it circled another point in space, and they kept adding these epicycles in order to make their theory fit their observations. And it does feel as if the dark matter, inflation, and dark energy are like epicycles that have been added. What do you think about that?
Yes, I mean it could be the case that we've been going down the wrong path for decades, because, as you said, so much is unknown. It could be that once we discover what dark matter is, we'll realize that we've been, on the wrong track for years. That's always possible in science. Sometimes there's small changes in science. Sometimes there are revolutionary ideas in science, and of course, with quantum physics, that came out of the blue. So it could be that whatever is the cause of dark matter or whatever is the cause of dark energy could lead to another revolution in science.
And there are real problems with the current Big Bang theory, the theory which has dark matter in it, which has dark energy and has inflation. And there's a thing called the Hubble tension, which somebody has actually just sent us a message about. And that is that the expansion rate of the universe, which we measure directly, or as directly as we can, when we look at galaxies and we try and see how fast they're moving away from us, is different from the expansion we get from extrapolating from the Big Bang. So we know there was a Big Bang fireball, and we extrapolate from that, and we get these two numbers, and they're different, and no one can see why they're different. Is this a point where maybe we're going to get some hint at some deeper theory that unites all these bolt-ons into one kind of seamless theory?
Well, I think we need to be careful. I think there needs to be more experiments done on measuring the Hubble constant, and if these experiments continue to show a discrepancy, then we might have to rethink the physics. But that's an interesting point, because back in the days of Hoyle, the Hubble constant was widely different than it is today,
and that determines the expansion rate of the universe. That's right, the Hubble constant.
Right, the expansion rate of the universe was very different back then, and back in Hoyle's time, when he proposed a steady state model, the Big Bang model was predicting that the universe was only about 2 to 3 billion years old. And of course, we knew that Earth was older than that, and the stars are older than that. So that was a big flaw in the early Big Bang theory, was that it relied on this Hubble expansion rate that turned out to be off by significantly. Turned out there was some error in calculating distances using the Cepheid variable stars, that they had to be recalibrated. So it could be that something in our cosmic distance ladder today telling us what the distances are to various galaxies could be wrong. So we might have to recalibrate that, how far things are in the universe. There might be something that's an unknown factor. It could be a simple error, or it could be a fundamental rethinking of science. It's hard to say at this point.
Let's just get back to Hoyle, because Hoyle never gave up on the steady state theory. He never believed in the Big Bang, and he constantly modified his steady state theory. And he realized that, in fact, matter, he thought, was not created uniformly between the galaxies, but there were bursts of matter formation. And his theory has kind of ended up kind of similar to the current picture, because in the current picture, we have inflation. And basically the idea is that there was this inflationary vacuum. The universe began in an inflationary vacuum. So the vacuum has a higher energy state than its current ground state. And this energy state had a really weird property. It had repulsive gravity. And so this vacuum started expanding faster and faster. And it was kind of a weird thing, like, if you had banknotes, I had a stack of banknotes between your hand, you pull them apart, you get more banknotes. And that's what happened with this inflationary vacuum. You get more and more of it. It's called the ultimate free lunch. But as it expanded ever faster, it was a quantum thing. And in random places, it decayed into normal vacuum. And the energy that was of the inflationary vacuum ended up creating matter and heating it to very high temperatures. So all over this ever-inflating vacuum, there were small Big Bang universes. So the Big Bang is not just a one-off. They're happening all over this inflationary vacuum, and we just happen to be in one of them. And that, to me, seems very similar to how Hoyle ended up.
Yeah, so Hoyle was partly vindicated. And when inflation came out, Hoyle said, aha, that's what I've been saying all along, is that the matter and energy in the universe was not created all at once, but is created through these quantum processes. But Hoyle I think some people said Hoyle maybe should have leapt onto the inflation bandwagon and took partial credit for it. But instead he said, well, I don't really believe that you could have this era in the early universe that would start and then stop abruptly. We need something that's continuing. We need something that's measurable today, not something in the distant past. So Hoyle liked the idea that inflation disrupted the old Big Bang, but he didn't really believe in the inflationary universe model because he wanted something that could explain all the cosmological observables through something contemporary, something measurable today, rather than something from the past.
Now, someone's asking about string theory and whether that's compatible with the Big Bang. I should say that we really don't know about the actual origin of the universe. We know that there was this giant explosion in the past, and we can follow in our theories. We can follow what happened after that. But the actual moment of creation is kind of beyond our abilities at the moment, basically because we have a theory of the very large things, which is Einstein's theory of gravity, and we have a theory of very small things, which is quantum theory, and they need to be united because when the universe was born, it was very small. It was smaller than an atom. So we need a quantum theory of gravity to try and explain that event. We don't have that theory. We don't really even know how to get that theory, although string theory is an attempt to get that theory. And so the ultimate questions like, what was the Big Bang? What is space? What is time? What happened before the Big Bang, if that's even a meaningful question? These are still unanswered, which makes science exciting to me. I hope it does to you as well, Paul.
Yeah, so those are fascinating questions, and uniting quantum theory with gravity would be an amazing leap forward in science, but we're very far from doing that. And string theory is elegant because it leads to a theory of something which includes gravity as a possibility, includes the graviton, which is technically a spin +2 particle. It produces something like that in the mix, but it also produces, string theory today produces so many other things that are not detectable. So we have to kind of weed out all these things, all these types of particles that don't exist, and narrow it down to say, well, it uniquely predicts our universe today. So some people like string theory because it's elegant mathematically, but then other people say, well, it's not really testable, and even some of the low energy predictions of it haven't really come true yet. So that is one of the frontiers, and looking at what happened in the early stages of the Big Bang, or even if there's a before the Big Bang, these are frontier areas, and it's really hard to say where they'll go.
So I'll just really finish. Thank you so much. I'll just finish by saying how incredibly lucky we are to be alive today. Previous generations would have killed for the kind of information that we have. We can see to the edge of the observable universe. We can count up the content of the universe, which is about 2 trillion galaxies. And we also know that it all burst into being in this giant fireball called the Big Bang 13.82 billion years ago. I mean, absolutely incredible that we're at that stage. And we probably have a chance within the next 10 or 20 years of answering some really fundamental questions like, what was the Big Bang, what drove the Big Bang, what is space, what is time. So it's an incredibly exciting time to be alive. So I'd just like to thank you, Paul, for being my guest today. It's been really fantastic talking to you. And please join me again in a month's time. We'll do this again with another guest and another fascinating topic. Thank you very much.
Thank you. My pleasure, Marcus. It's wonderful talking to you too. And I agree with you. It's a great time to be alive in cosmology.
Thanks.